Greetings, students. This is allLogarithmsEqual with a lesson on perfect square dissection. Without further delay, let's get right to it. Now, perfect square dissection is, as it sounds, a practice of splitting up a geometric square into smaller squares that fill its entire area with no remainder. The result is sometimes called a squared square, since we're breaking it up into component squares, and these component squares are sometimes called elements of the squaring. And so I think there are a lot of things to consider in this mathematical problem. And the first thing I'd like to mention is that really there is no requirement that has been stated about the number of squares we use, and it turns out to be a very interesting kind of piece of information, I think, to determine how many squares you need in order to actually have a perfect square dissection. But there are a few specific definitions that I'd like to go over before we continue.
So a dissection is called perfect if each of the component squares is of different side length. So let me write that. And it is called simple. We can call a dissection simple if no subset of component squares, or elements, forms a complete rectangle. So again, the whole idea of a square dissection of some kind of shape that we start with is that, we're breaking up the original shape into component squares called elements. And the reason we'd like to impose these kinds of constraints is because if they weren't there, we'd get some relatively trivial results. For instance, we could, in theory, keep dividing up a square into halves. Like, if we suppose we started with a square, we can simply divide it up into 4 elements, or component squares of equal side length, and say that we're done, or say that we're finished right there. Or, for instance, we could also just choose a bunch of 1 by 1, unit squares, just to sort of fill the entire area of our original shape, whether that be a square or a rectangle. But have we really gained anything from doing that? Instead, we can actually get some thoughtful, beautiful results if we make the goal a little less orderly, or at least less obvious. So keeping these thoughts in mind, we can create a diagram that sort of organizes what kinds of square dissections exist. And while it won't be too extremely important for this video, it gives us a way of classifying different dissections. So I'd like to draw out this sort of dichotomy, if you'll bear with me. So on one kind of axis, we have perfect and imperfect, which are, of course, opposites. This is just describing this first property right here, whether it's perfect or not perfect. And then on the other axis, we can specify, well, a dissection may also be simple or not simple, which we can also say is compound. And so with these definitions set up, we can actually consider a kind of, this is what I was alluding to. It's basically a table that sort of organizes these dissections, and it gives us a way of classifying them. This is just one way of classifying them. There are actually many different ways of describing square dissections, but this one I sort of like just as a starting sort of thing, because we can see, let's just take it one by one. For the upper left corner, I'll actually sort of draw this out loosely. The edges of the table, I guess. But so basically for the upper left panel, we get what's called a simple perfect, and very often you might see squared square or squared rectangle. So I'll just say, for the specific case, it's SPSS, which is a simple perfect squared square. And for the upper right case, we actually get SISS, which, and really it's the first two letters that are particularly of importance, and that is, simple imperfect squared square. We could also have squared rectangles or, other kinds of shapes that we're actually dissecting. But this is the important bit of it, the fact that we're classifying it. And if it's compound imperfect, one could perhaps see that as, or, write that as CPSS. In other words, it's a compound perfect squared square. So, and we'll see examples of these, of each of these in a moment, actually, or at least later in this series. But what I wanted to draw your attention to, for one thing, was this bottom right case, which turns out to be somewhat of a trivial case. Because, if we think about it, for these particular dissections, if they're imperfect and compound, what that really means in this context is that we're really not imposing any restrictions on the dissection. In other words, we're not requiring that each element has a unique side length, and we're also not requiring that there is no subset of squares that form a rectangle. So, in other words, for this case, there are so many trivial examples of imperfect square dissections, especially if we allow them to be compound. Because the ones that I described earlier, well, yeah, maybe this is a bit of a misnomer, because perhaps not all of them are trivial, but this at least contains some trivial cases. So in other words, filling up, our starting square or starting rectangle with a bunch of unit squares, that would be allowed as a compound imperfect dissection. So, it's somewhat, at least in my view, less interesting, because we're really not specifying any specific restrictions. Now, that being said, there are, as I said before, other ways of classifying dissections. So there may be some other special properties of dissections, even if perhaps they are compound imperfect. But, I digress. This is sort of, we'll see those cases later, or I'll address those cases later, but I'm not quite there yet. But just to begin this investigation, let's consider a perfect square dissection. And, one thing that you might try to do is actually to sort of make your own perfect square dissection, just on your own. So if you'd like to try that, that is one option. But I'd like to sort of give you a bit of a warning that it is particularly challenging if you're not given additional information. But there are different approaches to doing these things, and hopefully I get to those later. It might help you to play around with this idea yourself and to make a perfect square dissection. But you'll get an idea for how challenging this kind of mathematical problem is. And it turns out that each of these, I'd also like to say that it turns out that each of these kinds of categories, you could say, or each of these types of square dissections have their own property, and this is a property I haven't brought up yet, which is called an order, basically. So each dissection has an order, which specifies the number of component squares that are used in that order. So the number of distinct squares in that dissection is its order. And each of these types, now obviously you need to specify whether you're talking about squared squares or squared rectangles. There's a slight bit of a difference in the sense that a squared square is a subclass of the squared rectangle. But the point is, yes, of course, each type of dissection, as long as we specify which kind of dissection we're talking about, there are kind of unique properties, and each of them actually has a unique number that is the minimum order needed, in other words, the minimum number of squares needed in order, to have perfect squares, or simple perfect squared squares, they require a certain number. Hopefully I'll put it on screen, I hope, because I haven't quite memorized all of them, but I know it's a specific number of components in order to actually exist. And so, excuse me, there are no simple perfect squared squares, in other words, square dissections, that use a number less than that number of squares. I hope that's clear. I apologize if it's not. But in other words, you need a certain number of squares, typically a large number of squares, in order to even have one of these square dissections that actually adds up to a square. And the same goes for rectangles, too. If you have a squared rectangle, you need a certain minimum number of squares for such a dissection to exist. But normally it's a little bit easier with rectangles, as you might imagine. For instance, it can be proven that there are no perfect rectangle, in other words, perfect rectangle dissections that have order less than 9. And I believe that refers to simple perfect rectangle dissections, but I'll check. Now, to give you a sense for the history, this topic originated from a more general idea of splitting a rectangle into component squares. So in other words, the more general idea, splitting a rectangle and having a rectangle dissection, that one came first. A Polish mathematician by the name of Morone first published this idea in 1925, which, I don't want to necessarily impose my own, perspective on the history of mathematics to others, but at least I will at least state it. You don't have to agree, but at least in my view, that's a somewhat recent date when it comes to this sort of thing. Okay. Is this audio still working? Let me be right back. Yes, it is. Good. Okay. Alright, this is going pretty smoothly. Now, specifically, this Polish mathematician discovered a perfect rectangle dissection, a dissection that split a single 33 by 32 unit rectangle into component squares, each of which had a unique area, as you can see. So it was it was a perfect rectangle dissection. And I'm going to try to show you, I think it was this one. I could be wrong. Alright, so I had a couple of printouts that I wanted to show you. So in the upper left, you'll see a 9-square rectangle that, and by the way, these first two images on the top, they come from Wolfram Math World. And so obviously I'll put all these links and a bunch more sources in the description. Many more sources in the description. But the point is, in the upper left, you'll see a 9-square rectangle that implies that the order is equal to 9. So we're using 9 squares in order to, and we're arranging them in order to basically sum up to a rectangle in terms of the area. And so it's a dissection of a rectangle, as I said before. And interestingly, a Russian mathematician, Luzin, who had made advances in set theory and analysis, made the remark soon afterward that it would be impossible to do the same thing starting with a large square as the frame. In other words, instead of a rectangle. And, of course, as it happens, Luzin happened to be wrong on this one, as Roland Sprague, I think, is how you pronounce that, found the first perfect squared square, in other words, the first perfect square dissection, of side length 55, so in other words, the original, total square had length 55, and he found that in 1939, which I think, I could be wrong, but I think that's the diagram right below it. It's much larger, obviously, and has a much higher order, but the side length is 55 in this particular case. So that should be, I could be wrong. So today I'll be presenting a few different theorems about these squared shapes. Firstly, I'll be presenting them. Unfortunately, I can't exactly prove all of them yet, but I hope that this will be, an introduction to a nice series about them. Firstly, it was proved in 1940 that in other words, that no one can square a rectangle using less than 9 elements. So as it turns out, I mentioned this earlier, I suppose, but the original 1925 dissection was it's the first one I showed you in the upper left, was one of, I think, one of two rectangle dissections that exist using 9 squares. In other words, 9 component squares. And there's only 2 of them. This is one of them that he discovered. And it used the minimum number of elements possible as well for a perfect square or perfect rectangle dissection. Secondly, a major theorem is that for every possible dissection of a rectangle into n rectangular elements, so in other words, we're starting with a dissection, we're considering a dissection, a rectangle dissection, of order n, there exists a corresponding CNet with n plus 1 edges. Now, this is an interesting theorem, but the more I research it, I find that the further I dig, the more complicated it gets. But it's very interesting. It has to do with graph theory, is really what we're talking about. Because a CNet is also known as a polyhedral graph, it turns out, which is formally a 3-connected simple planar graph. And really, the more I learn about graph theory, I'm thinking of making a new series just dedicated to it, honestly. It's very interesting. Really, somewhat of an underrated branch of mathematics. But what this means, when I say 3-connected simple planar graph, I'm going to go into this probably in another video, given how long this is becoming. But if we remove any 3 vertices from the graph, the remaining vertices must still be connected. So that's essentially what I'm talking about when I'm talking about a polyhedral graph. And then we can remove a single edge from this CNet and obtain a very important graph, one that can represent a square dissection of a rectangle. And how we do that, and some other things that accompany it, involving linear algebra and matrices and things like that, I can hopefully talk about that in a future video if you'd like me to. But just know that it gets very interesting, and we can link this mathematical problem directly to graph theory and to some linear algebra things, and it's pretty interesting. This is something I think that we can all agree is a valid, interesting area of mathematics. After all, it's purely geometric. It only requires us to use natural numbers. And furthermore, we could measure the sizes of the elements with quadrants as well as distance. So my guess is even reformists like Dr. Wildberger would approve of this sort of thinking in mathematics. And lastly, this branch has had relatively recent developments, as I mentioned earlier. There's been a lot of developments ever since 1925, but even onward into the 1960s and even the 21st century. It's very interesting. So I conclude there is likely room for more development in this field, and if you have any questions or findings, let me know. And of course, thank you all for watching. It is my hope that I can inspire each of you in one way or another to continue learning about these topics in your spare time. And that being said, I'll also link to all those sources, because trust me, I found a lot of sources about this, as you'll see. You'll be pleased to know this video is not brought to you by any large multinational corporation. Anyways, thanks for watching. Sources are in the description, and hopefully I'll get some new updates for you soon.